So, today, это мы whiteboard, да? It's okay, whiteboard with black, yeah? So, today is 19. Okay, I will close the window. It's that will do. So, and today I would like to discuss with you, I think that one of the most interesting, I should say, and the important issue related to the basics of neutrino physics, and in particular, neutrino spin, or neutrino mixing and oscillations in presence of matter. Neutrino mixing and oscillations in presence of matter, in matter. So if you probably recall, just remember what we have discussed on our last lecture. This lecture was devoted to coherence in neutrino mixing and oscillation phenomena. And a great deal of that discussion was devoted to the description of interplay of two waves corresponding to two different neutrino species. And I think that you got a knowledge of feeling that what is very important for understanding the nature of neutrino mixing and oscillation phenomena is the relation between the energy and momentum of neutrinos. This is a key issue. Yeah? So, what very important, and this relation is sometimes called the dispersion relation, the relation between energy and momentum. Yeah? The dispersion relation for a neutrino, for a particle, like the energy depends on the momentum. This is very important issue, yeah? And what about matter? What we can say without any calculations, any deep investigations, but from our knowledge, from other phenomena where this relation takes an important, play an important role. I would like to recall the case of the photon in vacuum. The photon, the quantity of electromagnetic radiation, the photon in vacuum. This very simple relation between energy and momentum, yeah? The energy of the photon is just the modulus of momentum. So the mass of the photon in vacuum is 0, yeah? And what happens with this dispersion relation in matter? In matter, we know that the mass of the photon is not 0 due to interaction of a photon with the particles of the environment of matter. So it means that there is quite different to the vacuum case relation between the energy and momentum of the photon in matter. This is the mass plus the momentum of the photon. So, the presence of matter, the interaction of photon with particles of environment, with matter, violate very easy, very simple relation. And due to this, the mass becomes non-zero. Just taking into account this, knowledge, we can expect that also in the case of neutrinos propagating in presence of environment with which a neutrino participate in some interaction, will also violate the relation between the energy and momentum for the neutrinos. And as a result, we can suppose that the presence of matter will change their neutrino mixing and oscillation pattern. This is our knowledge, and now I'd like to realize this with you during this our lecture. Well, let me recall neutrino mixing and oscillation in vacuum. Just because we will finally arrive to the situation when we see how the relations that describe this mixing and oscillation phenomena in vacuum is disturbed or violated by the effect of neutrino interaction with particles of the environment. That's why I would like to recall you. So, mixing in vacuum, mixing and oscillations in vacuum. So, again, we consider two mass states, we call them physical states, nu1 and nu2, that correspond to the mass 1, mass 2, and there is flavor neutrinos that participate in the interaction Lagrangian. These particular neutrino species are produced in the source and are detected by observing some interaction with other particles. These flavor neutrinos, we confine ourselves to two neutrino cases, electron and mu neutrino. And we introduce mixing. So we postulate that the flavor neutrino is a superposition of the mass states of neutrinos, and the mixing matrix can be parameterized by one quantity, the mixing angle, and can be chosen, this matrix, in the following way. Cosine theta, theta is the mixing angle, sine theta minus sine theta cosine theta. So each of the flavor neutrinos is a superposition of the mass states of neutrinos, neutrino 1 and neutrino 2. So evolution equation of the physical states has the following form: I d over dt, the physical neutrino, the Hamiltonian physical neutrino, and the Hamiltonian is just the energy zeros of mass states, where alpha 1 or 2, and the energy for these neutrinos, I just write the relativistic equation for the energy momentum relation. Okay, this is a Hamiltonian. We postulate it by hands. It's more or less reasonable, yeah? So then we expand this, accounting for the case that all neutrinos are always relativistic in our consideration, and we just take into account only for the first two terms in expansion for relativistic neutrinos. And for the evolution Hamiltonian, evolution for these physical states, we get the following. There is something that's proportional to the unit matrix that is not important at all if we consider the problem of neutrino mixing and oscillation and calculate the probability of conversion between different flavor states, or the survival probability. And this, I will just write it for completeness. This is the modulus of momentum, or this is the energy, plus this sum of mass squared of two neutrinos divided by 4 multiplied in the denominator to the modulus of momentum. This is a unit matrix plus or minus mass square difference divided by 4 modulus of momentum, or this is the energy, 1, 0, 0, minus 1. So what is important really that this part is diagonal, and it means as a consequence the neutrino of the mass 1 and 2 are the eigenvalues for this Hamiltonian, and they survive forever. So they survive forever, yeah? Okay, just accounting for mixing, so we can express these physical neutrinos through the mixing matrix and flavor neutrinos. We substitute this guy here, and we obtain the evolution equation for the flavor neutrinos in the following form. In particular, I d over dt, or you remember that we can substitute the evolution in time to evolution in space, because we are dealing with the relativistic neutrinos, yeah? Okay. So this is the flavor neutrino state equals to the evolution matrix, Hamiltonian, U, H, U cross, as we call this Hamiltonian prime in vacuum. It means that this is evolution Hamiltonian for flavor neutrinos in vacuum. It can be easily calculated using the expression for the evolution Hamiltonian for the mass states and using the expression for the mixing matrix, UF. And we get immediately that in vacuum, I just stress, we never indicate before this vacuum. We just only use H prime. Now I just would like to distinguish this case from another one that we shall discuss during our lecture when we deal with this Hamiltonian in matter, yeah? And then we just substitute this vacuum to the matter indices, yeah? So, and this Hamiltonian is as follows, equals to minus, I have to recall this mass square difference. This is the mass square of the second minus mass squared of the first neutrino, minus mass square difference divided by 4 modulus of momentum. And here is a matrix minus cosine double theta, sine double theta, sine double theta, cosine double theta. Okay. And we have obtained the probability of oscillations between electron and muon neutrinos in the following way. The probability of oscillations as a function of x, I will just write here x instead of t, yeah, for relativistic neutrino case, equals to the amplitude of oscillation sine squared double theta multiplied by sine squared mass square difference divided by 4 neutrino energy x. Neutrino energy is equal to momentum, modulus of momentum of neutrinos. This is the probability. That is the final point of the story. The only thing I would like to introduce here, if you know the elements of the Hamiltonian of evolution for any type of neutrino oscillation or any time of neutrino mixing in oscillations, not only we are considering now, but also for another type of oscillation, for instance, for neutrino spin or spin flavor oscillations that we'll discuss in the next part of our lectures next year. Yeah? So if we have this Hamiltonian in vacuum in the form, this is H I G H I G H G I H G G. Well, this is the particular case, just parameterized by this H. Well, then the probability, the amplitude of oscillations can be expressed. We just sorry, I have to sine squared double theta equals to H I J plus H J I squared divided by H J J minus H I squared plus the same what is denominator H I J plus H J I squared. This is what we can use always like this. And sine squared double theta m squared divided by 2 energies x can be expressed in the form of oscillation length pi x divided by oscillation length oscillation length, where this oscillation length equals to 2 pi's divided by the square root in the denominator 2 H I J squared plus H I minus H J J squared, and everything all this square root. So if we know the elements of the evolution Hamiltonian, using these general expressions, we immediately can write the probability of oscillations. We can define or calculate the amplitude and the second term that describes the harmonic evolution of the probability due to neutrino propagation along the x direction. We shall use this expression just in our further considerations. So, now let's turn to our main problem that was announced already, and let's deal with the particular case of two neutrinos, neutrino electron and muon, propagating in matter. We should specify the properties of matter. And let's specify neutrino electron to neutrino muon oscillations. In matter. We consider an ordinary matter that is composed of electrons, neutrons, a point-line particle. We neglect the structure, the fact that neutrons are composed of quarks. Yeah? We shall consider neutrons as a point-line particles. And protons is a normal matter composed of electrons, neutrons, and protons. So, and we introduce the so-called particle number density. In Russian, число частиц в единице объема. Particle number density, the number of particular particles in a cubic centimeter. Particle number density. Particle number, this is really a number, density. So this is number of electrons in a cubic centimeter, this is a number of neutrons in a cubic centimeter, this is a number of protons in a cubic centimeter. This is normal matter composed of these three particles. This all matter here, the desk, our body, the sun, stars, etc. Of course, if you consider extreme conditions with the high temperature or huge densities, you should account for the fact that neutrons and protons are not a point-line particles, they composed of quarks. But we shall neglect this. We shall consider neutrino scattering and interaction with electrons, with neutrons and protons, and consider neutrons and protons as a point-line particle with which neutrino participate in interaction, scattered, following the electroweak theory, and in particular we shall go to the local theory of weak interactions following the Fermi theory. Yeah? So, and we have to consider how different two neutrino flavor states interact with electrons, neutrons, and protons. In addition, we supposed that the matter is neutral. Matter is neutral. It means that the number of electrons in a cubic centimeter is equal to the number of protons. It's normal matter. Normal matter on the Earth, normal matter in the Sun, and of course we are very interested in particularly one of the applications of our studies applications is the study of neutrino fluxes from the Sun. So we consider matter composed of two types of particles, and in addition we consider that matter is neutral. So, and now we have to specify and to derive the consequence of neutrino interaction scattered on these particles. And following to the analogy with the photon in vacuum and in the matter, we can expect that these interactions will change the effective energy of neutrino in matter in respect to what we have in vacuum. So we can suppose that there will be a violation of the vacuum relation between energy and momentum, and some additional term that we call this effective energy or potential energy will appear and will enter the relation between the energy and momentum. That is our goal, and this goal just determines the direction of our consideration. So, and we start with the standard model Lagrangian. We start with the standard model Lagrangian that accounts for interaction of neutrinos with these particles. First of all, with electrons. I think that from the general courses of electroweak theory, quantum field theory, you more or less recall the structure of the standard model Lagrangian, in particular in its part related to interaction of neutrinos with electrons. Do you remember this? Can I address to this your knowledge? I can write Lagrangian, but I would like to use this Lagrangian to start calculating a particular diagram, Feynman diagram, that contribute to effective energy of neutrinos due to interaction with electrons. I think that I can start with this, not recalling, not writing this full Lagrangian, yeah? Because you will immediately understand what I'm meaning, yeah? So, and the interaction of neutrinos with this set of particles can be classified within two different types. The first type of interaction is called the interaction of charged currents. And the second type of interactions that contribute to the effective energy of flavor neutrinos due to their interaction with the electrons, neutrons, and protons is the interaction of neutral currents. And I will just write a Feynman diagram, and you will immediately understand and recall, probably. Yeah. So first, let's consider the charged current interaction. And here are the brackets: interaction, contribution, to effective energy of electron, and we have two, and muon neutrino in matter, composed of these two particles, three particles in matter. So first we consider the charge current interaction, and I will write the typical diagram that just follows from the standard model Lagrangian of interaction with electrons. First we start with the electron neutrino. For the electron neutrino, we have the following diagram as a consequence that's included, that starts straightforward from the structure of Lagrangian. So this is the initial neutrino of momentum P2. This is the electron with momentum P1. This is minus, this is W plus boson, this intermediate boson. And here we have the electron of momentum 4 and neutrino, electron neutrino, is momentum 3. So this is a typical diagram of interaction of electron neutrino with electrons. Let's write the mathematical expression for this diagram, just addressing to your knowledge of the standard model Lagrangian. I will write exactly accounting for coupling constants. Yeah. Also, we write the following. This I just write. This is delta to the standard model Lagrangian due to this particular diagram. This is a shift of Lagrangian, yeah, additional term due to this interaction. And we just write charge current to the case of electron neutrino. Yeah? Okay, we write the following: I j square root of 2 in the denominator squared. J is the coupling constant. There are 3. J, J prime, E, the electron charge. Yeah? Or you can substitute 1 by the Weymouth angle. Yeah? But, okay? And here, why it's called charge current, you remember? This is a charge current. So the initial neutral particle is converted to a charge particle. This part of the diagram is called the charge current. The same is here. And the intermediate boson is charged. So charge current interaction are due to emission and absorption of a charge boson. Interaction of 2 charge currents. You know this, yeah? Okay. So this is the wave function bar of left-handed electron. So I just immediately exactly reproduce this notation. This is 1 divided by 2. This is left, 1 minus gamma 5. The wave function of electron transformed, conjugated, gamma 0. This is a normal notation that is used. Yeah, you know this. Okay? Then the gamma, the Dirac matrix, lambda. There is a summation over this lambda. This is the left-handed electron neutrino of momentum P2. This is a charge current. Yeah? And then between there is a propagator. Yeah? It can be expressed in the following way: minus I G lambda rho, summation over G over lambda and rho, in denominator P2 minus P1 squared minus the mass of W boson. This is the green function of W boson, but we also include or exclude a second term that is suppressed in the case when energy is smaller than the mass of the W boson. This is not a low energy approximation. You remember there are 2 terms. Yeah, only this survives. Yeah, if the energy is not extremely high. Yeah. Well, okay, and here is the second current that can be written in the following form: nu bar electron left, neutrino electron, over the momentum 3, gamma rho is summation over lambda rho, and the electron left P4. So this is an interaction of 2 currents. interaction of two currents. And if we also neglect the momentous in respect to the masses, taking into account that the mass of W bosons is very, very high, so we can write here that this is approximately has the following form: minus 4 Fermi coupling constant G phi F Fermi square root of 2 electron left P1 gamma lambda neutrino electron left P2 nu bar electron left P3 gamma lambda summation over lambda electron left P4. So this is the local, the result of considering these interactions as a local Fermi interaction. So instead of this diagram, we just consider now this, the local Fermi coupling, and F equals to G squared divided by 8, then the mass of the W boson in the denominator over the square root of 2. So this is a local interaction of two currents. This is following to Lagrangian of Fermi, local weak interactions. So now I would like to ask you to check that it is possible for this particular structure of expression, it's possible to change the positions of the fields. And this was shown by Firth transformations. So we just, I would like to ask you to check how it is possible to check. So this is the bispinal, yeah? Four components. This is also 4 components. This is 4 by 4. How you recognize this? You should sum this 4 by 4, multiply by this bispinal, yeah? And then multiply by this. If you pull indices to all of these 3 guys, there are 2 indices here, 1 is here, 1 is here, yeah? And summation over these repeated indices. The same, you can do this. And then you can, once you put indices, you can change the position of all these guys. And you can recombine them in another way. And I will write in which way you will get a final result. This is exactly what was shown by Firth for the first time. But there are a lot of different other structures that accounting in which the gamma matrices exist. Also, it is possible to change the positions of the fields. So we can write it that this is exactly the same as what I am writing now for Fermi coupling, constant, square root of 2 in denominator, then electron left bar, P1, gamma, lambda, electron left, P4. So it is possible to change positions of electrons and neutrinos correspondingly. Please check. This is a just straightforward relation. Yeah, and here is the part that contains the electron, the neutrino electron left P3 lambda rho gamma lambda neutrino electron left of P2. So this is more or less the final expression that describes the result of electron-neutrino interaction with electrons of the background. Now, the initial state of this particular process is composed of two fields, electrons and neutrinos. The final state also composed of electrons and neutrinos. And we are interested how this particular part of Lagrangian change or shift the effective energy of particular neutrino. So it means that in doing this, we have to sum up over the electron states. And then we shall get the shift of the effective energy of neutrinos due to interaction with electrons of the background. Do you understand? More or less. Yeah? Okay. So, we have average over the electron states. We have average over the electron states. We should use the vacuum electron wave functions and make an average. So I will just, so plus, yeah? So what we have to do, we have derived an addition to the effective Lagrangian, yeah, and we have the following. So we have a state of initial state and final state composed of electrons and neutrons. Here is the Lagrangian. We have derived charge current, electron neutrino, and this is, so we have to calculate this summing up over the electron states. We shall use the vacuum wave functions, operator wave functions of electrons, and use the following prescription that after this summation we can write that if we make the summation over electron states, we shall get that this is neutrino wave function, the energy of electron neutrino due to interaction with electrons, and here is electron neutrino. So, and after that, we can write that the charge current interaction of electron neutrinos with electrons of the background result that the addition, so here I should put, I think, the Hamiltonian, the corresponding Hamiltonian. It's better to write here. So the addition to the Lagrangian of interaction due to charge current for neutrino case, electron neutrino case, is equal to minus square root of 2 coupling constant Fermi, the number density of electrons in the background, neutrino electron left, gamma 0 neutrino electron left. So here we use the following. So if we consider this guy, this is the number of electrons. This is the density of electrons. Following to analogy between the electromagnetic current and the quantum mechanical current, yeah? This is the density, the number density of electrons, yeah? Do you understand this? Or not exactly? So, not all. Okay. What I would like to recall here, yes, to recall. So, let's consider the continuous relation in electrodynamics, yeah. Classical electrodynamics, classical so we have d rho over dt plus divergence of the current equals to 0, yeah? This is current, electromagnetic current. This is the density, charge density, yeah? So, okay, if we consider a quantum electrodynamics, and in particular the Dirac equation for a charged particle. Huh? So the electron in a magnetic field, for instance, yeah? So we have to make this substitution. The momentum should be transformed in the following way, plus the charge of electron, the momentum, the potential of this external field. The potential of this field is like this, the scalar and vector potential, yeah? Okay? And the Dirac equation for this case has the following form: gamma p mu plus E0 potential mu minus the mass equals to 0. Okay? This is Dirac equation. Then we can introduce alpha matrices equals to gamma 0. It is matrices, Dirac matrices, alpha and beta. Beta is just gamma 0. Then we can write the following in a more direct way: I d psi over dt equals to minus I alpha nabla psi plus E0 alpha momentum potential, vector potential psi plus m beta psi. Yeah? If you just multiply this by psi cross, and if we write a similar equation for the psi cross minus psi cross divided by d psi cross I over dt equals to I nabla psi cross alpha plus E0 psi cross alpha vector A vector plus m psi cross beta. And if we just multiply the first by psi cross and the second by psi, and we can, from this, we can get the following equation: d over dt psi cross psi plus divergence over psi cross alpha psi equals to 0. If we just finally multiply by the charge, we can get that the density of the charge equals to E0 psi cross psi, and the current equals to E0 psi cross alpha psi. This is the density. And this is current. So I think that it brings light to the definition that this is really the particle density, yeah, and this is the current. So this is analogy with the electromagnetic classical electrodynamics, yeah. So it means that no, we just exclude this, but this depends on the normalization factor. Yeah, psi cross psi equals to n, the number densities in a unit volume. Yeah, and this is current. So I think that I just give some insight to this. Yeah. So just to continue. So here we suppose here that matter is at rest. So non-moving matter. This is important. So we just only account for the zero component here, yeah? Only, we do not account for vectors. Alpha vector that is proportional to the gamma Dirac matrices vector, yeah? So what is important? We consider non-moving matter or non-relativistic matter. This is usually people use this approximation. I would like to say that just many years ago, when I started just thinking about this, and I proposed that it's possible also to account for the motion of matter. And with my postgraduate students and postgraduate students, we generalized this approach to the case when matter is moving, and have found very important changes in the neutrino mixing and oscillation pattern due to relativistic, possible relativistic motion of matter that can be found. This relativistically moving matter can be found in astrophysics. And we published several papers, and at least two of my students got their PhD degrees accounting to these effects of motion of matter. They generalized this, the case of non-moving matter. So this is the final story, how interaction of electron neutrino with electrons shift the effective Lagrangian. Now let's finalize the story about the charge-current interaction, and let's recall that we have another guy, a muon neutrino. We should also consider what will be the outcome for this case when we consider muon neutrino. Muon neutrino in electrons, and we consider charge-current interaction. So, and we should recall the Standard Model and say that, immediately say that contribution to the muon, in the case of muon, the shift of the Lagrangian due to charge-current interaction with electrons is zero, exactly zero, because there's universality between electron and neutrinos interaction, and electron neutrinos interaction interact with electrons, and muon neutrinos interact with muons. But there is no muons in our environment. It is exactly zero. So we have no such diagram with the case of muon neutrino. Yeah, here it should be muons, but we have no muons. You understand? Yeah. And the diagram of like this doesn't exist at all. This diagram in the Standard Model gives zero result, because there is no interaction between muon and electron, muon neutrino and electrons, no. Because in the Standard Model, if not to think about account the neutrino mixing and oscillation, the flavor is a good quantum number. It's conserved. But once we introduce the mixing between electron and muon neutrinos, we violate the flavor conservation law. In Mach, we know that there is no flavor number conservation law due to neutrino mixing and as a consequence oscillations. But in the initial Standard Model, that do not account for neutrino mixing, because we just mixing is additional term and extra, like a hat over this huge building of the Standard Model. It's additional part. But inside the Standard Model, there is no such a diagram. There is no possibility to change the number of flavor states in initial and final states. Yeah. Okay. So this is the end of the story. So there is nothing to be added for this zero contribution term. Now let's turn to the case of neutral currents. And consider interaction due to emission and absorption of neutral bosons, dead bosons. Obviously, the charge current interaction is mediated between two charge currents. This interaction is mediated by charge bosons. Neutral current is mediated. And the diagram, in this again, in the Standard Model, the particular diagram is like this. This is initial neutrino. It can be electron or muon neutrino. And this is the final neutrino. It can be whether electron or muon neutrino. It can emit neutral Z boson. And here it can couples to electrons, muons, but we have no muons at all. So you just make this cross. We have no muons in normal matter. Muons can appear in a reasonable amount under huge temperature and huge density. In some extreme environments of the early universe or in some catastrophic events in astrophysics, probably some muon can be present in a reasonable amount in the environment. But in normal matter, there is no muons. And also, indeed, the standard model couples, this boson couple to quarks. But again, we neglect the neutron and proton structure as a compound states of 3 quarks, but we put here neutron and proton. Neutron and proton, considering this particle like a point-length particle. And so it means that the Z boson couple one of the quarks of the neutron, one of the quarks of the proton, but we just do not take care about this. And now we can write, and you can then say that the contribution is equal to both neutrinos, contrary to the charge-current interaction. Now we just neutral current interaction, and we can write that the contribution of the neutral currents to neutrinos of any type, whether it's electron or muon, doesn't matter because the same diagrams, equal diagrams, appears here. Is minus, again, we consider a local theory. We just make like this with the Fermi coupling instead of propagator of Z boson. Yeah. So for Fermi constant square root of 2 in the denominator, and here we just write the fermion bar. So I have introduced the fermion can be whether electron of the background, neutron, or a proton. This is one of the particles of environment. So I don't want to really put here the momentous. Yeah, this gamma lambda. This is I3L. This is a constant, a kind of charge. This is the third component of which is a spin. This is a charge, like on of charges, yeah, of the standard model of electric weak theory. 1 minus gamma 5 divided by 2. This is a real electric charge, sine squared Weinberg angle multiplied by this one of this F, this whether is electron, neutron, and proton. So again, this is one neutral current. The initial state and the final states have the same zero charge, and this is the second neutral current, yeah, because the initial electron and final electron have the same charge. So due to interaction, the charge is not changing. So this is called the interaction of two neutral currents, yeah. And this interaction is mediated by the charge charge zero boson. Yeah? Okay. And here is a part that corresponds to neutrinos. Neutrino bar left, gamma lambda, neutrino left. Okay? This is the addition that arises to the standard model Lagrangian for different two neutrinos, electron, muon. This is the different two contributions of three particles interaction with our electron and muon neutrinos. Yeah. So this is not 4, this is L. Yeah. So and now just taking into account the known values for these charges, there is a spin third component and the charge. We can write for these particles, we have electron, proton, neutron. I just like this table. Yeah. So here we just put this, the third component of weak as a spin. This is a charge. For electron, minus 1/2, charge minus 1, for proton plus 1, for neutron 0, 1/2, minus 1/2. So this is the set of charges that contribute to this Lagrangian. Huh? If we just sum up everything, we can write that delta L neutral current for two types of neutrinos, I do not specify because it is the same, equals to minus square root of G Fermi multiply by the sum over the particles of the environment, electrons, protons, and neutrons, the density of each of these particles, the number density of electrons, protons, and neutrons, then the third component of weak in the spin, F minus 2 sine squared Weinberg angle multiply by the charge of each of the matter components, brackets, electron bar neutrino left, gamma 0 neutrino left. Again, we are not interested in the moving matter. There were only the zero component of the current remains. Understand, yeah? Because if you just account for gamma 1, 2, 3, it will correspond to the moving matter, in particular to the velocity component of matter in direction 1, 2, 3. But we neglect. We say that the velocity of matter, or speed of matter, or matter is not moving, is zero, yeah? There are only the zero component of the current remains here. Okay. Now, we would like to sum up everything and to simplify, reasonably simplify this expression. Why? Because first we should consider that the number of electrons and protons are the same, but the charges, electric charges of electrons and protons are opposite. It means that the term proportional to the charge in this part will cancel out. Yeah? Also, we see that the third component of weak is a spin for electron and proton are also have the same number but in the opposite sign. So it means that from this game, from this particular term, electron and proton contributions cancelled out due to specific nature of weak interactions, due to the fact that these two charges for electron and protons has opposite sign, equal by value but opposite sign. So it means that only the contribution to the cross-section of, or to the effective Lagrangian due to weak interaction with neutrons remains for electron, mu, and neutrinos. And they will be the same. So therefore we can write, so I have to put plus, yeah? So finally, what we can write? That the neutral current contribution to two neutrinos, electron or muon, can result in the following shift of the standard model Lagrangian. So delta L neutral current equals to minus sum for L equal to electron or muon, because we have two neutrinos with the same contribution, but we have some all additional terms to Lagrangian, in general Lagrangian, that describes both electron and muon neutrinos. Yeah? So this is sum over electron muon neutrino, and here is neutrino bar L left, gamma 0, the potential for neutrino of the type L, neutrino electron L left. Where? For this, where? Where? For the potential for electron neutrino in particular equals to square root of 2 G Fermi and E. So I just write here and also charge current interaction. Yeah, I sum up the obtained contribution of neutral currents plus what we have discussed for the case of electron neutrino interaction with electrons, the charge current contribution, both contributions when sum up. Yeah, so this is from the charge current interaction plus or minus 1/2 the number density of neutrons. This comes from neutral currents. So sometimes this can be written like this. And for the effective potential for muon neutrino, we get only this term, because the charge current doesn't contribute due to specific structure of matter, composed of electrons, neutrons, protons, no muons, and the equal number of electrons and protons. This is a very specific but very natural structure of matter. Minus square root of 2 in denominator, the coupling constant, and n. This term comes from neutral currents. So I think that we need some probably 10 minutes more, yeah, okay, to finalize. So finally, accounting additional contribution to the Lagrangian due to charge current and neutral current interactions, we can modify the vacuum Dirac equation for the neutrino wave function. So in vacuum, we have okay, this equation comes from the standard model. Now we add extra term here due to neutral current plus charge current, and the equation will be modified. The same procedure, you know, this Dirac equation can be derived from the Lagrangian. Yeah, we calculate an extra term, and we can modify this equation, accounting for interaction of neutrinos with the particles of the environment in the following way. This is gamma 0 P0 minus gamma P vectors minus m multiplied by the wave function equals to gamma 0, this potential psi. So this is due to interaction with environment, and we can rewrite this in the following way, that gamma 0, let's put sorry. Gamma 0, gamma 0, P0 minus potential equals to gamma vector, P vector plus M. Then we obtain that a new dispersion relation accounting the interaction of neutrinos with background environmental particle, electrons, neutrons, and protons, equals to the mass squared plus momentum squared plus potential. This is the result. So it seems like, it looks like neutrino get an additional potential energy. Yeah? And what is the energy? This is contribution to the Hamiltonian. So now we can turn directly to the neutrino mixing and oscillations, and we shall deal with this within 5 minutes. Okay. The remaining 5 minutes just to close this story. Yeah? So we have found that really the dispersion relation is modified, and we can know what is V. Okay? Can I? Okay. So now what about mixing and oscillations? In matter. What about mixing and oscillations in matter? So, in vacuum. So, in matter. In matter, if we have some A accounting for the effect of matter, we shall put wave. All numbers, all values with wave, it means that this particular quantity or characteristics of the vacuum case, additionally accounting for the matter effect. Yeah. So, in vacuum, I just recall once again the equation for Flavor-Neutrino evolution. This is Flavor-Neutrino H, the prime neutrino. Okay. Now in matter, very reasonably to write the same equation, d over dx, neutrino flavor equals to the Hamiltonian in matter multiplied again neutrino flavor. So this is the modified due to neutrino scattering of electrons, protons, and neutrons of matter, the modified evolution Hamiltonian. Why we do not put wave here? Because by definition, by meaning, the flavor is not influenced by the fact whether matter is present or not. The flavor state, this is very important, the flavor state is determined by the standard model Lagrangian, like this, neutrino electron, and this is W boson. For instance, for flavor equals to air. So this is the definition. So, and this definition is not violated by presence or not presence of matter, is invariant. So therefore, the flavor states are the same. in the case of presence of matter or in vacuum. You understand? Because the definition, how we can check, how we can observe, how we can produce the flavor state by this interaction that comes from the standard model Lagrangian. There's nothing about whether matter is present or no. In this point, electron and W produce electron neutrino, or electron neutrino disappears with the appearance of W and boson and the electron. No any way to include the environmental conditions. No, this is determined universally whether matter is present or no. Therefore, this is evolution of flavor states are the same as a vacuum. In presence of matter, the Hamiltonian is changed due to flavor interaction with the environmental particles. Yeah? And by where the Hamiltonian in matter, once again I will stress this is a Hamiltonian in matter equals to the vacuum Hamiltonian of evolution of flavor states plus what additional energy we have derived, like a potential energy, plus the following square root of 2 Fermi constant and E minus 1/2 and N 0, 0 minus G Fermi and N. Why here zeros? Because there is no coupling between different flavor neutrinos. Yeah, understand? So this coupling is diagonal in flavor basis. This is important, yeah? This is important. So now, what is this guy? I don't want to repeat the formula of the first hour transparency here, just in the first 5 minutes. I don't want to repeat. We derived this many times, and I repeated in the very beginning of our meeting today. Yeah? And finally, I can write, we get the following, that this Hamiltonian matter equals to, I don't want to skip part that's not important for considering neutrino probability oscillation probability. I put all parts of the Hamiltonian starting with one that is proportional to the unit matrix, that is not important for oscillation probability. So this is the energy. So I would like to be, I'm sorry, I just use sometimes energy or P0 and energy is the same. This is energy of neutrino plus the sum squared of masses, m1 squared, m2 squared, divided by 4 neutrino energies, minus equal part that contribute to both neutrinos, that is proportional to the unit matrix also. This is the number density of neutrons, 1, 0, this is unit matrix. And this comes from interaction of the electron and the mu neutrino with neutrons. But this is the same, this is proportional to the unit matrix. Only electron component remains, yeah? So it means that only charge current interaction of electron and mu neutrino for mu net 0 contribute to the shift of the oscillation probability in matter. Only interaction of electron neutrino with electrons. Okay. Because interaction with neutrons is proportional to the unit matrix. And some part of interactions with electrons and protons cancel each other, yeah? Okay, the neutral contribution, okay. Plus mass square difference divided by 4 neutrino energies. Here is minus sine double theta, cosine, sorry, cosine double theta, sine double theta, sine double theta, mixing angle in vacuum, yeah? Cosine double theta. Okay? So, sometimes this part is called 1 over 2 neutrino energies m wave squared. This is not a square of some guy. This is just a definition. You understand, yeah? Where, I will write what it is, plus where. This m wave squared equals to exactly 1/2 minus mass square difference cosine double theta plus 2a, where we introduce a equals to 2 square root of 2 G Fermi, the electron number density and the energy. This is where matter is present here. This is a matter contribution to the effective neutrino evolution Hamiltonian in presence of matter. Yeah, this is mass square difference, sine double theta, vacuum mixing angle, mass square difference, sine double theta, mass square difference, cosine double theta. So, now I again would like to recall how we write the probability of oscillation once we have derived the Hamiltonian in the form 1-1, Hamiltonian 1-2, Hamiltonian 2-1, Hamiltonian 2-2. We know all these terms now. And also, maybe on the 10th minute of our meeting today, I just show you how the final expression for the probability can be expressed through these 4 guys. Yeah? If you know them. We have derived this now. This is elements of evolution Hamiltonian accounting for matter effect. Now we can write immediately the final solution for our problem, this oscillation probability. Electron neutrino to mu neutrino in matter composed of electrons, equal number of protons, and an arbitrary number of neutrons. Yeah? We can write it in the following way. This probability in matter equals to sine squared double theta in matter. So the mixing angle is modified, and I will show you now really how this theta depends on the density. Multiply by the sine squared. I repeat the formula that we have derived, pi x oscillation length in matter. Oscillation matter. So the formula formally looks like for the vacuum case. The only change is there is a wave above the mixing angle, so the mixing angle is modified, and the oscillation length is modified. Two main features or guides that govern this oscillation probability of neutrino flavor oscillation in matter are modified. And where? I just express this mixing angle and show exactly how it depends on the density of environment of the electron component. Where the amplitude of oscillation, sine squared double theta, is equal to, in the numerator, mass square difference, sine double theta squared. This is a characteristic of neutrinos, mass square difference and the mixing angle in vacuum. In the denominator we have mass square difference, cosine double theta, minus a squared. Yeah? Plus mass square difference, sine double theta squared. This is the amplitude of oscillations, and it is really modified. If you just switch off an E to 0, A to 0, and theta becomes the mixing angle in vacuum, as it should be. If you just derive something, you count into extra property or effect. If you just rule out effect, you should derive to initial situation when this effect not accounted for the very beginning. Everything is okay. And what is the oscillation length? What is the oscillation length in matter? Also depends on density of electrons. 2 pi's divided by long expression, square root of mass square difference divided by 2 energies, cosine double theta in vacuum, minus square root of 2 G Fermi, density of electrons squared, plus mass square difference divided by 2 energies, 2 energy of neutrino, sine double theta vacuum squared. This is in denominator, this is a square root. This is the final solution for our problem. How the presence of matter composed of electrons and protons with equal number, with equal density, and orbital number of neutrons violate or change the neutrino flavor neutrino oscillation pattern, formulate структуру, in case when we account for interaction of electron and neutrinos with these particles. The formula remains the same, only the mixing angle is changed and the length of oscillation is changed. Now my final remark, and I would like to address your special attention to this. What we can see, this is the amplitude of the oscillations, yeah? And it's exhibit a remarkable resonance behavior. If A, the resonance, I don't want to go to another sheet, the resonance in neutrino oscillations, when double mass square difference cosine double theta in vacuum equals to A, and I will recall that A is 2 square root of 2 Fermi constant and electron E. Yeah? If is fulfilled, so this guy is 0. It means that numerator and denominator are the same. It means that in this case, the amplitude of oscillations is 1. The maximal mixing. It doesn't matter what is the mixing angle in vacuum, what is the mass-square difference. Let's suppose the neutrino with particular energy. We fix the energy. The mass-square difference is given by nature or by the God, I don't want. The theta, the angle, is also fixed by nature. It's not in our hands. And we consider particular source of neutrinos with a particular energy. It's also beyond our control. So, for any value for mass-square difference, mixing angle, and for particular neutrino source that correspond to particular neutrino energy, always there is a density that results that A equal to this guy. So it means that if you span density over the whole range from very high numbers to 0, you always will see on this range of changing of density a particular number density that realizes the maximum mixing of flavor neutrinos. And this is resonance in neutrino oscillations. So, and this was a resonance was first predicted and observed theoretically by two gifted Soviet Union Russian scientists, Mikheyev and Smirnov. And they published a paper in 1985, Mikheyev and Smirnov. Yuri Smirnov is still without Mikheyev. Stanislav Pavlovich has passed away some 5 years ago, maybe 10 years ago. At first, this effect was called by academician Lev Okunin, a famous Russian particle physicist. He called this effect Mikheyev-Smirnov effect. But just very soon, in a year, this name was corrected because Hans Bethe wrote a paper, a Nobel Prize winner, by the way, American scientist. He just recalled that Mikheyev and Smirnov use particularly the same calculations I reproduced during this hour with you, that are addressed to an earlier paper of American Wolfenstein. Leon Wolfenstein. So this resonance now is called Mikheyev-Smirnov-Wolfenstein effect. Эффект Михеева-Смирнова-Вольфенштейна. Или the resonance in flavor oscillations, or resonance flavor oscillations. Resonance always. Resonance because really for this particular number density of electrons, this guy kills and the amplitude becomes maximal. And this effect should be used, and now is used, to explain or just to understand the observed flux of neutrinos from the sun. So in order to properly understand what is seen in the present experiment, when the fluxes of neutrino are detected from the sun, you should use this effect, because inside an inner part of the sun, where neutrinos, electron neutrinos are produced, the density is very, very high. And on the corner, it's come to 0. It means that for a wide range of neutrino energies, corresponding to a particular range of spectrum of electron neutrinos from the sun, neutrinos pass through this region inside the sun, when density is exactly kills this mass square difference multiplied by the mass by the cosine double theta in vacuum. So the resonance effect should be counted, but there are some, not confusion, but the experimental confirmation is not very accurate enough. Still, there is some flexibility, but nevertheless, the present solution of the Solar-Neutrino problem due to this effect is called the large mixing angle Mikheyev, this Smirnov-Wolfenstein solution of Solar-Neutrino problem. So this is an official title how the Solar-Neutrino problem, you remember it's about 1/3 of electron neutrino is observed in the flux of neutrinos from the sun. But this is large mixing angle because this, before, maybe 15 years ago, maybe even 15 years ago, it was not obvious whether this mixing angle is big or small. But now the mixing angle between the first and the second neutrino that corresponds to the oscillations between the electron and muon neutrinos, that is completely quite enough to solve the Solar-Neutrino problem. It is enough to confine oneself for the case of two neutrinos, electron to muon. It gives a very, very good, a very accurate solution for the Solar-Neutrino problem. Initially, it was supposed that maybe its angle is small, maybe not small. It was discussion whether large or small. There was also small mixing angle solution, also was discussed before. But now, after experimental achievements and also the knowledge and feeling and understanding this Mikheyev-Smirnov effect should be counted, this is an official way how to solve the Solar-Neutrino problem. This large mixing, it's not small. Right? The mixing between the first and the second neutrino is not small, contrary to the mixing between the first and the third one. It's 10 times more smaller. It's very small, yeah? Well, this large mixing angle plus Mikheyev-Smirnov-Wolfenstein should be counted, in fact, solution of Solar-Neutrino problem. So I think that probably we shall stop here. Yeah? This is like a final point of our discussion, and I am very happy that we managed finally to reach the goal, because I have planned that we have stopped this semester on the effect of neutrino oscillations in presence of matter. And also I'm happy that I just managed, due to all our obstacles, we managed to arrive to final step I planned we should arrive. So, thank you very much.